We talk a ton about the green energy transition, but what if the answer to our massive energy storage problem is actually hiding inside the very infrastructure of our fossil fuel past? In this explainer, we're going to look at something straight out of a sci-fi novel. It's happening right now, right beneath our feet, at a fully operational pilot project at Fraunhofer IEG in Bochum, Germany. We're talking about taking a literal relic of the coal era and completely transforming it into a cutting-edge solar battery.
Okay, let's dive into this. Picture a massive colliery headframe from back in 1954. This towering industrial symbol of an era that was built entirely on extracting dirty fossil fuels. Well, fast forward to today. Sitting on that exact same geographic footprint is a gleaming, ultra-modern 30-kilowatt concentrating solar collector. It's pretty wild to think about. We are literally seeing the past and the future of energy sharing the exact same coordinates. It's a total 180-degree pivot, from digging up carbon to capturing clean, renewable sunlight. Now, the researchers working on this have such a fantastic, almost poetic way of framing the whole thing. They describe it as creating benefits for eternity from burdens from industrialization. I just love that. Usually, abandoned coal mines are treated like massive environmental liabilities, right? They're burdens, they're dangerous, they need constant monitoring. But this project, it completely flips the script. It challenges us to look at this giant hole in the ground, not as a scar on the earth, but as a permanent, incredibly valuable green asset. Let's put some hard numbers to this transformation, just to wrap our heads around the scale. Between 1953 and 1958, this specific colliery pulled out over 37,000 tons of coal. Think about that. That is a staggering amount of carbon extracted, burned, and pumped straight into the atmosphere. But compare that historical carbon-heavy output to what it's doing from 2023 onwards. Today, it is providing completely CO2-neutral heat storage. It went from being a massive contributor to climate change to a zero-emission heat supply system. The sheer irony of using a coal mine to actually fight climate change? Absolutely brilliant. So how exactly does a coal mine magically become a green energy asset? Well, it becomes what we call an underground thermal battery. Just picture the old empty mine galleries deep underground acting like a giant, naturally insulated thermos. See, one of the biggest headaches with renewable energy is intermittency. The sun is blazing hot in the summer when, frankly, we don't need to heat our buildings, and it's weakest in the winter when we absolutely do. This thermal battery is the fix. It lets us capture that intense summer heat, trap it in water, and stash that hot water deep down in the earth where the natural insulation keeps it nice and toasty until winter rolls around. Let's move forward and see how this builds step by step, because it's a beautifully elegant loop. Step 1. That modern solar collector up top captures the sun's energy and heats up water right there at the surface. Step 2. This hot water is injected straight down 64 meters underground right into those old mine shafts. Step 3. The heat is stored in the existing mine water, safely trapped in the void down there. And finally, step 4, when winter hits and the campus is freezing, that stored hot water is pumped back up and the heat is recovered to warm the buildings. It's a remarkably simple concept, really, but executed through some serious engineering. Now, what's really interesting here is getting a visual sense of what's hiding right beneath everyone's feet. Above ground, you've got perfectly normal modern buildings and all the lush greenery of the Fraunhofer IEG campus and the nearby university. But superimposed down below is a massive, invisible network of the old colliery galleries. It's like an entire subterranean world that was just sitting there, idle and completely forgotten, that's now been reawakened to serve as a high-tech energy storage facility. You might be wondering, okay, but is there really enough space down there to actually make a dent in energy usage? Oh, absolutely. When they dug out all that coal back in the 50s, the miners left behind an estimated void volume of over 27,000 cubic meters. That's a lot of empty space. The researchers calculated that even if they only use a super conservative 10% of that leftover space, they can store roughly 165 megawatt hours of heat every single year. And why does that number matter? Because 165 megawatt hours is exactly enough to cover the entire annual heat demand of the Fraunhofer IEG facility. Just 10% of this old mine can theoretically heat the whole campus. All right, let's anchor this in some hard engineering data, rapid-fire style. To make this whole system hum, they had to reach the deepest level of the colliery, so they used their own drilling rig to punch 3 separate boreholes exactly 64 meters deep. That's your production and injection depth. 64 meters, straight down into the dark. Next crucial number, 60 degrees Celsius.
Naturally, the water just sitting in these abandoned mines is a pretty chilly 11 degrees. But by running it through those concentrated solar power collectors on the surface, they literally supercharge that water up to a maximum of 60 degrees before sending it back down into the earth.
And finally, €899,219. That is the total cost of this pilot project, funded through the Heat Store Geothermica AeroNet initiative. I bring this up to prove that we aren't just looking at some pie-in-the-sky, theoretical white paper concept here. This is a fully funded, physical reality that actually became operational in 2023. Real money is testing real, tangible solutions.
And the crazy part? They aren't stopping here. If you look at the hardware specs, they're currently running a 30 kilowatt solar collector, but the plan is to double that capacity to 60 kilowatts. The current water flow rate into the mine is 7 cubic meters per hour. They're going to more than double that to 15. Add in a variable high-temperature heat pump with a capacity ranging anywhere from 100 to 500 kilowatts, and you've got a system that is actively scaling up to capture and distribute way more green energy.
So the crucial point here is efficiency. I mean, it's one thing to pump heat down a hole in the ground. It's a totally different ballgame to actually get it back out effectively. The team is constantly tracking pressure and temperature data using a network of existing groundwater monitoring wells. Their main goal, like the golden metric for this entire pilot, is to hit a 50% heat recovery efficiency. If they can successfully pull back up half of the heat they pumped down there, the resulting drop in CO2 emissions is going to be absolutely massive compared to relying on conventional district heating, natural gas, or oil. And this brilliantly illustrates why the BOCM project is so incredibly important for the big picture. It isn't just about keeping one single campus warm. The data they're pulling from this very site is basically serving as a master blueprint. The ultimate goal is to take this tech and significantly enlarge the development of mine water underground heat storage across the entire Ruhr region of Germany. They are literally paving the way for a massive regional shift in how we store energy. Which leaves us with this final, incredibly exciting thought to ponder. The Ruhr region alone is just packed with former collieries, many of which happen to be right next to existing district heating systems. If this underground thermos works efficiently in BOCM, and frankly, all the data says it's well on its way, how many other abandoned mines are quietly waiting beneath our feet right now? Think about it. How many scars of the Industrial Revolution are just sitting there, waiting to be transformed into the giant clean energy batteries of tomorrow? The potential to rewrite our energy infrastructure from the underground up is absolutely staggering.